not unheard of that there's mathematicians that have done the work for you a while ago. So if you can define what you want precisely, for example, you want to, or at least conceptually, what do you want, and then if you need to look for it maybe. But okay, as it turns out, okay. So just to be more specific about what I'm saying is so if f was a polynomial, right? So what would be the max degree such that f can be just evaluated at endpoints, okay, and that the integral is exactly, okay, that's important, is exactly the sum of, you know, some coefficients wi times fi. Alright, so you take the sum over I of the product of some numbers times fi, and that would give you the function. And the degree that you can, the max degree that you can do it, at least with a polynomial approach, is going to be 2n minus 1. So 2 times n minus 1. Alright. But then you have to figure out what the weights are and where you should evaluate f. So the reason you need polynomials to do this is because, as it turns out, okay, this is where the black magic shows up. If you use x, the x values as the roots of the Legendre polynomial of degree n, okay, and then the weights are equal to 2 over 1 minus xi squared, which is, so I'll just write it like this, even though, okay, let's write it like this. So, okay. So it's 2 over a bunch of stuff. The first factor is 1 minus xi squared. The second factor is the derivative. I'll just call it p n prime at xi squared. So if p, capital P, is the Legendre polynomial, and you take the derivative and you evaluate it at the roots of the Legendre polynomial, you take the square, you multiply it by 1 minus that root square, and then you divide 2 by all of that. That will be the weight. Okay, seems pretty random, doesn't it? So that's why I don't want to go exactly into the details. So right, I'm just looking at my notes just to make sure I don't miss anything. Okay, so the first thing that you can see in that is that we need to find the roots of something. We need to derive polynomials. We need to compute some polynomials, like, you know, the Legendre polynomial of degree n is an actual set of coefficients. It's like 3x minus 1 or something. It's a concrete polynomial. And so you have to figure out what it is, or to at least to know what it is, right? You have to derive it, you have to evaluate it at a value. So all that we did for polynomials can kind of be used. And so what you have to understand is that the first time I did this, I sort of started with wanting to use this method of integration, which is called the Gaussian quadrature. And then I figured out that there was this, I could do it instead of sort of hacking it. I could introduce this concept of polynomials, and introducing that concept was useful for the code. It clarified some stuff, because you don't actually need polynomials at all, because the formula for computing the Legendre polynomial, since it gives you the whole polynomial, you can always sort of it's hard to explain, and I feel like I might be losing many of you, but maybe because it's just words, right, with no visual support. But okay, so let's just be quick about it, just say it. Okay, the way to compute the Legendre polynomial can be written in such a way that you don't need to talk about coefficients. You can just evaluate the polynomial as you go, so there's no need to store the coefficients. It can always be polynomial at a value, which is just a number. So you don't need the concept of a polynomial, but it's nice, and it like mathematically speaking shows up in other places. And also, if you compute the polynomial, then you just have a thing, the polynomial, that you can use. Whereas if you compute the value, every time you have to recompute the value. Is that a problem? I don't know, but there's no real advantage to it. You know, it's just if you don't know how to formalize the notion of polynomials, then you don't formalize it and you just hack it. It might be fine, but if you know, it's one of these things. I think for some other things, hacking it is not such a bad idea, because before you know how to make a solid concept in the computer, I don't know, it's a case by case thing. So okay, we have to compute the roots, right? And mathematical knowledge tells you that the root, so you have how many roots? If you're a constant, you have no roots. If you're a linear function, you have one root. Parabola, 2 roots. So it's the degree of the polynomial, right? So you have n roots and the ith roots. So if you just pick one root, it's going to look, it's going to be close to the cosine of pi times I minus 1 over 4 over n, which is a degree, plus 1/2. Okay. It's also going to be between cosine of pi I minus 1/2 over n plus 1/2 and cosine of pi I over n plus 1/2. Okay, then polynomial, the Legendre polynomial at point x can be computed recursively. So if you know the first Legendre polynomial and the second Legendre polynomial, you can find the third Legendre polynomial. If you know the second and the third, you can find the fourth, and so on. So here's the formula. It's 2 times n minus 1 times x times p n minus 1, so the previous Legendre polynomial at x, everything's at x, minus n minus 1 times the one before the previous, so n minus 2 again at x, and this whole thing divided by n, so 1 over n times this whole thing. Okay, and then you need the starting point, so the polynomial of degree 0 is taken to be 1, and you can take the polynomial of degree minus 1 to be anything, for example 0. Okay. You could also